pleasure and honor to be here this morning. Very special day, July 14th, for the people of France and for all our French colleagues. And it's particularly big honor for me to introduce our speaker today, Dawn Tilbury. She got all degrees in electrical engineering, the first one from University of Minnesota, and then master's and PhD in electrical engineering and computer science from University of California, Berkeley. And she joined faculty of College of Engineering of University of Michigan in 1995, but as professor of mechanical engineering, and now she has joint position in both mechanical engineering and electrical engineering. This is significant because this somehow, when I follow her career, this combination somehow set up her incredible enthusiasm and devotion and opportunities, challenges, everything which one can think of for interdisciplinary and particularly collaborative research. And she has been active in all these societies, and she is fellow of IEEE, fellow of ASME, and life member of Society for Women in Engineering. She has been a recipient of many awards, including early career development from NSF, but also from American Automatic Control Council Ackman Award. And she is focused, and her passion is in broad applications of control systems, in particular to applications to robots and to manufacturing, as you will hear today from her talk. She has been very instrumental in developing and in growth, which is impressive growth of facilities at University of Michigan. She held position in research of the College of Engineering of University of Michigan. And now, what is the most fascinating about Dawn Tilbury, she will be head of the whole entire engineering directorate at National Science Foundation. In her position, she will oversee 6 divisions and almost 100 different engineering programs. And with her background and her expertise and her passion for collaboration, this is just tremendously beautiful challenge and opportunity for Dawn to lead that kind of task of shaping engineering in the United States, but also globally. So I, as a director of National Science Foundation's, sat in welcoming Dawn. He said, I'm thrilled to welcome that kind of leadership. So today we will listen about her passion, and her talk will focus on sharing those applications of cyber physical manufacturing systems. So please join me in welcoming Dawn Tilbury, and floor and stage is yours, Dawn. Thank you.
Well, thank you very much, Bojena. And I'd also like to thank the organizers of this wonderful conference for inviting me to speak to you here today. I hope you've been enjoying the conference and this beautiful city of Toulouse. Today is our last day at the conference, and so I'm very happy to have the opportunity to speak to you before you all leave. So my talk today is about hybrid processes for controlling cyber-physical manufacturing systems. And in the intro to this talk, I'll try to explain to you a little bit about what I mean by that complicated title that's quite a mouthful. I'll start by describing some of the challenges that I've seen in controlling manufacturing systems. And then I'll talk a lot about simulations, because we use simulations in manufacturing as well as most people do when they're doing control. Finally, I'll talk, the main part of the talk will be about control methods for reducing the downtime in manufacturing systems, and I'll give a few different examples of that. And finally, I'll conclude with some future work. So I think many of you are familiar with manufacturing. You can see a quote here for the US, it's about 12% of our GDP. You can also see from the map that the US is not alone in having manufacturing being a significant part of their GDP. In fact, for most countries in the world, manufacturing is very important. You can think that manufacturing creates value. It takes raw materials and adds value to those to create finished products. So it is one of the ways that countries can create value and improve their economy. So therefore, it's an important topic for consideration. If you look at studies about manufacturing across the world, they indicate that in most plants, the overall equipment effectiveness, meaning the amount of time that the system is adding value or creating parts, is only about 60%, whereas world-class would be considered 85% or higher. Now, 100% is not achievable because there always needs to be some time for the system to be maintained, to change over from one part to another, to change the workers between shifts. So 100% is not attainable, but 85% is seen to be highly possible. So our job in control is to try to increase that equipment effectiveness from 60 to 85%, which shouldn't be that hard. You can also read the studies that show that even a small amount of increase in effectiveness can save a lot of money for the company, meaning that they can create more value and pass those savings on to consumers so they can have lower prices for their products. So let me talk a little bit now about a few different examples of manufacturing systems. So in Michigan, you may know, we make a lot of cars still. And here's an example of a powertrain manufacturing plant. The picture is from Ford Windsor, which is just across the river in Canada. But in a powertrain plant where they make engines or transmissions, most plants have about 100 operations to go from a raw casting to a finished part. Now these meter scale parts, think the size of an automotive engine, have micron level tolerances, so the quality is very important. And one way they achieve that high quality is through very high levels of automation. In fact, you won't see very many people in most automotive manufacturing plants, not in the powertrain side. It's mostly automated where the parts move from one machine to the next, completely automated. And they go through these machines where the system will produce one part every 20 or 30 seconds. So quite a high volume. If you do the math, that ends up to, several 100,000 engines per year. So these plants are highly complex, but this periodicity where the parts go through the machines in a certain order reduces the complexity because you can look at each machine independently. The high tolerances required for quality, as well as the dependencies between stations, are important to consider for control. Another example that might initially seem very different is semiconductor manufacturing. But here again, when you look at how many steps it takes to go from a raw wafer to a finished chip, it's on the order of hundreds. So not so different from the number of steps that it takes to go from a raw casting to a finished engine. Now here the tolerances are quite strong, dictated by the reduced feature sizes that come about through Moore's law, where you cram more and more transistors onto every chip. Now, instead of machining operations, here we have complicated chemical and physical reactions at each stage, where you may lay down a mask and then etch and lay down another mask, etc., repeatedly. But again, you have these periodic stations where parts go through in a certain order. So although the processes are quite different, the system-level complexities of getting parts through the system, adding value to create a finished product, are quite similar to what you see in, say, an automotive powertrain plant. So for purposes of this talk, we're going to abstract both types of system and call it a large-scale manufacturing system, where you have raw materials coming in on one side, finished products going out the other side, and a number of machines in the middle. Now, PowerPoint doesn't let me draw 100 machines, but you get the idea. There's several machines that have to be gone through. Now, of course, each of these machines has its own controller to control the speed of the spindle or the amount of gas that's being ejected or the temperature in the chamber, etc. So each machine has its own individual controller. But at the system level, there's a system-wide controller, a supervisory controller, whatever you want to call it, but it's coordinating all of the different machines. And so the control goals that we want to achieve for such a large-scale manufacturing system are improve the overall quality or the yield. You can think of that as the number of good parts that come out that you can actually sell versus the number of parts that you actually make. That would include the ones that are scrapped. And the productivity, or the throughput. How many parts overall are coming through this system? Now, in my course that I teach at the University of Michigan, I focus on this feedback loop between the machine and the controller. And I'm sure many of you are familiar with that. And I will say there are still a lot of challenging problems in manufacturing that look at that specific level of the machine and the control to improve the quality specifically. However, in this talk, we're going to look at the supervisory level and abstract out what are the main ideas for the supervisory level, where the high-level controller is interacting with the controllers at the different machines. So I mentioned we want to improve the quality and the productivity to get this overall equipment effectiveness. So let me tell you a little bit about what this OEE is in a manufacturing system. So for each machine, you might imagine it could conceivably work full-time, and that would be the theoretical limit. Now, I mentioned the theoretical limit is not achievable 100% because of some planned downtime. You need to maintain the machine, clean out the chamber, lubricate the spindle, etc., change out the bearings. So that planned downtime can never be part of the overall effectiveness. So this is where you get the best case OEE would be about 80%. But as I mentioned, it's never 85% because there are all these other issues that come up. There could be unplanned maintenance. The machine could break and you need to stop and fix the machine. And that is unplanned, not part of the original schedule. You need to have some setup and adjustments, especially if you're changing between parts in the same line. There's some kind of setup that needs to be achieved. Then, if you're not working very effectively, there could be idle time while one machine is waiting for another machine to send it a part to work on. And these kinds of idle time can add up to a lot of downtime overall that can result in lost productivity. Also, you might have the machines not working as quickly as possible, and that might require more time to make the parts than could be achieved. Now here there's a trade-off, because if you work more quickly, you can make more parts, but your quality might not be as high. So there's always this trade-off between quality and productivity, and this is something that the engineers need to understand. However, in some cases, making the part more accurate might take more time, but does not give any extra benefit to the consumer. And so this needs to be understood from the engineering point of view. What's the optimal level of quality that you can get to have good productivity? And finally, the quality factor. If you start to work your machines too fast, the quality might not be good enough. They won't pass the test, and they either need to be reworked or scrapped. So all of these factors are contributing to reducing your OEE, or your overall equipment effectiveness. And this is what we're going to be looking at in this talk. And one of the big ideas is if we can reduce the unscheduled downtime where the machine is waiting for a part or is broken and needs to be fixed, then we can increase this overall equipment effectiveness, increase the profitability, and reduce the overall costs. That's the main idea. So in addition to this slide where I'm talking about how things are working while the plant is operating, there's the idea of what about building a new manufacturing system. On the top row, you see going from the concept for a new part or a new product to the design of a new manufacturing system and the refinement, etc. Now, there have been developed over the past 10 or 20 years many modeling and simulation tools that have reduced the time needed to design a new manufacturing system. In fact, you can build the whole thing in simulation and try it out and make sure that everything works perfectly. However, once you go from the simulation to the physical implementation, it's never exactly the same as it was in the model. And that's where there's this time required for the commissioning of the manufacturing plant before you move into the large-scale production. And there are opportunities that I'll talk a little bit about in this presentation today to reduce that commissioning time, the time between when the plant is built and when it's producing at full production, high-quality parts at high volume. So I said we're going to do control. Obviously, control implies feedback. If you have feedback, what data are you using for your feedback? Well, in a manufacturing system, you have data coming off of all of the machines. For example, positions, velocities, temperatures, forces, concentrations of gases, etc. All this data is coming off of the machines, has traditionally been going to those controllers for each machine and used to make local decisions. With the advent of high-speed networks and high-performance computing, we can now get all of that data off of the machine and up to the higher-level controller. What are we going to do with it? Well, we'll talk about a few ideas. In addition, at the high-level control, we can know what's the status of every machine. Is it running? Is it broken? Is it waiting for a part? What's the status? We have historical data. How has this plant been operating over the last hour, over the last month, over the last year? How have similar plants been operating over those time frames? How does my plant compare to other plants that are in my system? And simulation data. As I mentioned, there's a lot of simulations, and that data can be used for control. We'll talk a little bit about that. Okay, so for our feedback loop, we have some data, and then we have something that we need to control. So from the system level, what can we control? Well, you see the high-level controller there is interacting with other controllers. So it can adjust the reference inputs, the settings, the feed rates, the G code. It can also impact the schedules, What parts are we going to make today and tomorrow and next week? When are we going to do maintenance? When will we take this part down, this machine down to lubricate the bearings, etc.? So it's very high-level control that we're doing here with very high-level and very fine-level data. So we have some feedback data. We have some settings that we can change. Of course, if we're going to do control, we need some sort of a model. So one thing that you could think about doing is using a simulation model as the model for your controller. With high-performance computing, you can run that simulation model in real time and use it as something to try out different control strategies. This is commonly done in scheduling. In some cases, you may have first principles models that you can use to describe how the system behaves. And of course, we're well familiar with system identification, where we can build models of these relationships between the input variables and the output variables. And that's one of the things that I think is the most powerful idea in manufacturing control today, is to take this existing data that has always been there but has not always been easily accessible and put it together in new ways to get models that are useful for control. Models that we can use to improve that overall equipment effectiveness and increase the profitability of the plant. Now, I'm sure you've all heard this quote before, that all models are wrong. We're never going to get a perfect description of the manufacturing system. But if we can get useful models that can help us predict the way the system is going to behave or change in response to our inputs, and then we can use that prediction to determine the best control input, we can have a positive impact in the manufacturing community. Let me talk just a bit about the data that we're getting, and I'll do this in a very concrete way. So on the lower left there, you see a CAD model of a little test bed that we have in our lab at the University of Michigan. There's 2 robots and a big conveyor loop and 4 machine tools. You can see that the robots and the machine tools are all connected through this Ethernet switch. The variable frequency drive for the conveyor that determines the speed of the conveyor is also connected. We also have condition monitors. We monitor how much energy is being used by this system. And you can think that that might be a useful piece of data that might give you new insight into what's happening in the system. We have RFID that's on every part that tells us which parts are where and how things are moving through the system. And finally, other sensors, just generically listed there. We have cameras and many current sensors, force sensors, all kinds of different things that are going on. And right now, all of this data is going into the PLC, or the Programmable Logic Controller, that's coordinating the overall test bed. Now, we can pull that data out of the PLC into an on-site database and do some local analysis. But one of the exciting things that's been happening in the last few years is trying to get that data out of the plant. So we have worked with a company called Rockwell Automation that has what they call the Internet of Things Cloud Agent that can pull data from the PLC and then put it into a cloud storage. Once it's in the cloud, there are many different kinds of opportunities for analysis and visualization to understand not just how this plant is working, but as I mentioned, can you compare it historically? Can you compare it across different similar plants, or compare similar robots across different plants? So this is a new direction for getting data out of manufacturing systems and putting it in the cloud. I'm not going to talk too much about that today, but I thought it was useful to mention that this opportunity is now moving forwards in many different manufacturing systems. So now let me talk a little bit about simulations. So at the system level, you may have heard of these discrete event simulations. And I've just pulled here from the internet a little video of a Rockwell arena simulation that shows a high-level view of a manufacturing system. So in this type of a discrete event simulation, you can put in stochastic processing times for every machine, for every conveyor. How long does it take for the human workers to load the parts, unload the parts, etc. And once you build perhaps a beautiful 3D simulation model like this and add in all those statistics that you have taken from your plant, you can estimate what's the throughput of your plant, how many parts do you expect to make per hour, what's the reliability, how often do your machines need to be maintained, etc. So this is quite a powerful tool. It does not track quality very well because it doesn't simulate at the very lowest level. So unless you can represent quality with a statistical distribution, this is not going to address that piece of the overall equipment effectiveness. So another way to look at discrete event simulation is using something that we're very familiar with, which is Matlab and Simulink. So within Simulink, there's SimEvent and Stateflow that we've used to model machines with stochastic processing time. So you might end up with something that looks like this in your Simulink block diagram, where most of those blocks have stochastic timing and then events passing between the different blocks. And we can look at, for machines, mean time between failures, mean time to repair, how many parts are coming out of in each machine, capacity, etc. We can also abstract that into a Stateflow model, which is a much more deterministic discrete event, but the timing can be stochastic. So again, gives us much more of an academic framework to simulate the system level and the stochastics. Now we also want to simulate the continuous dynamics at the machine level. So continuing in the Matlab theme, this is a Simulink model in sim mechanics that puts together all the different joints and links of a robot, and then again has a very nice visualization of what that robot is doing. Now you can put this together very nicely in Matlab, and you can link it to the stochastics, where when the robot is called in the stochastic model, this particular simulation starts, and you can run these in parallel. There are also commercially available simulation packages for robots. For example, this one I'm showing here is called RoboGuide. It comes from Fanuc. Now this is higher fidelity than sim mechanics because it includes both the robot and the controller, and it's supplied by the robot vendor. On the other hand, it's a standalone software package, and it's more difficult to interface with other simulations. For example, there's no straightforward way to integrate this RoboGuide simulation with the arena simulation that I showed you earlier at the system level. So that leads us to some trade-offs that we have in simulation. In general, I put them into two categories. One is the vendor supplied, which are standalone solutions, but fairly high fidelity and commonly used in industry. And then there's the academic software, mostly Matlab and Simulink that we've been using, which are easy to interface and are built on solid mathematical foundations. Which type of simulation do we like to use? Well, we think both are valuable in their own way. And so we have projects that use both of these kinds of simulations. In this talk, I'll present a little bit more on the Matlab side of it, but both kinds of simulations can be very valuable. Okay, so now that we have these simulations and this data that's coming off of our system, how can we develop controllers to reduce the downtime? The first example that I'm going to give you is how can we reduce the ramp-up time or the commissioning time between when I've built this system and it's running at full production with high quality using an idea called virtual fusion. So people have been merging simulation and implementation for a long time. This is just a new twist on that idea. So you can imagine previously you build a simulation and then you go over and implement it. And it maybe doesn't work exactly the way you thought it would. So you go back and adapt your simulation some more, and then you implement it, and this is a feedback loop. Well, you can put the two together with what is called hardware in the loop, right? Where you're running your simulation and your physical implementation at the same time. One idea when you would do that would be to verify or validate some piece of the system before you build it. I'm going to take a minute and talk about the difference between verification and validation. From everything I've read in the manufacturing literature, at least, there's no commonly agreed upon distinction between these two terms, so I'm going to tell you how I'm going to use it. So to me, verification is when you have a mathematical model and use that model against a mathematical description of the specification to check that the model meets the specification. And to do this, you can use math or you can use a software to check the math. Validation represents the physical representation. So does the physical representation do what it is supposed to do? Again, against some specification that may be written in English, not math, and you would do a physical test to see if it works correctly. So what I'm going to talk about here is validation, using a physical representation of some part of the system and trying to show that it does what it is supposed to do. So validation has been used with emulated controllers and virtual environments. You can see a computer simulation of a controller there and a computer simulation of a plant. So for this type of validation, you would use the emulated control running on physical hardware with the simulated machines and robots to validate the controller. We're going to talk about the next step, which would be validation during commissioning. So commissioning is the phase of the manufacturing system design where you've built all of the machines, they're up and running, but you want to check that everything is working correctly before you put the parts through it. You can see in this picture of these large engine blocks that the parts are quite big and quite expensive. And if you break some of the parts during the testing of it, there could be some problems. A lot of cost could be incurred. So we want to try to run the system without the real parts to check the interconnections between the machines, the automation, the robots. But since the automation is set up to check whether the parts are there before it goes to the next step, we need to bypass or override these sensors. Now we can do that in software, but it requires a lot of extra programming. Sometimes people do it manually by, say, putting a picture in front of the camera to show that the part is there, or putting a coin on a proximity sensor to indicate that the part is there. Our question is, can we simulate the part and run the simulated part through the physical system to show that all the connections are being made correctly? So let me get a little philosophical here and talk about domains of existence. When I talk about the digital domain, or something that exists in a computer, a simulation, these things in the computer have essences and effects. The essence you can think of as data, digital information, and the effect is a change in that data. Now the physical domain, a part, has spatial essence. It occupies volume, and that's what's going to trip that sensor. And the effect of that physical volume is going to be the weight of that part or the physical, connection between the part and a sensor. What we're going to try to do is emulate that Newtonian effect through simulation by changing the value of the sensor. And if you believe, as I mentioned before, that all of the sensor data is available on a network, I just need to tap into that network and replace the sensor data with the simulated data. Instead of the physical weight that says 0, there's no part there, I'm going to change the value of the weight sensor to say the weight is 2 kilograms. It's just changing the physical essence with the data essence. So let's continue this philosophical discussion a little bit and think about what it means to go between these two domains. So we'll assume we start in the physical domain with a part. It has spatial essence. It exists in the real world, and therefore it has a Newtonian effect. It can interact with things in the physical world. And of course, it also has a data essence. It has a part number, it has some history, etc. So there's some data associated with this part. Now, it's not too much of a leap to say, okay, I'm going to take that physical part and put it into the simulated world. So now that it exists in the simulated world, it still has that data essence that tells me what part it is and what its history. Now, the leap is when I want to take that simulated part and put it back into the physical world. Now, it no longer has physical presence. It does not have that spatial essence. It doesn't physically exist. However, we want it to have that Newtonian effect. We want it to be able to trip the sensors as if it were really there. That's the trick. So how do we do that? We call it virtual fusion. So we have a simulation model of our part. Here I show a simulation model of a robot. And we have the physical plant. And what we want to do is take the output from the physical plant and the output from the simulation model and put them through a filter. And if one is present and the other is not, this virtual fusion filter is the one that should decide what should be sent to the system controller. And then the system controller sends the same commands to both the simulation model and the physical plant. So what we need to do, the trick, is to synchronize these two parts of the system. The physical plant is working in real time, the simulation model is working in simulated time, but we need to be able to synchronize those. You can see the effects that are coming from the physical plant are whether the sensor has tripped, what's the weight of the block, what does the camera show in the image, and the simulation model is giving the same types of essences because it also has a simulation model of the plant. And now the virtual fusion filter is going to determine which of the simulated inputs is it going to take and which of the physical inputs is it going to take and send those filtered outputs to the controller. And hopefully you can see that in general it'll be some mix of what's coming from the physical plant and what's coming from the simulation model in terms of what are we trying to integrate between the simulation model and the physical plant. So the test scenario that I'm going to go through is we have, again, the small test bed we have at the University of Michigan. We have a single work part that has an RFID tag, so we're going to need to simulate the RFID number. The conveyor is going to move accordingly, and the pallet stop, etc. So the essences that we have are the proximity and the RFID, and the effect is what is the command going to be sent to the robot. So in order to synchronize time, which is a tricky thing to do because simulations usually either run faster than real time or slower than real time, but here we need them to work in lockstep with the time on the wall clock. We use this tool that was developed by Rockwell Automation. And again, we have the PLC that's connecting on both sides. And this is the implementation you see on our physical test bed, where we have the simulation environment, where we're simulating the part and the RFID tags. And that data is going through, first being synchronized, and then being filtered, and then sent to the controller over the Ethernet link. So when you look at it in the physical world, we have, in the actual system, there's no RFID being read because there's no part on the pallet. But in the simulated environment, the RFID tag is being read because there's a virtual part on the pallet. So the virtual fusion filter puts those two together, and the system controller thinks there's a part there because it sees the RFID tag being read. Obviously, this is just a picture of what it looked like. But we were able to demonstrate that by simulating the work part with the rest of the system, we could filter the outputs and effectively run the system with a simulated part. And what this allows us to do is eliminate the cost and the waste of running off a system because we can do it first with virtual parts. And then, of course, again, you need to do it with real parts. It's not going to eliminate the step of real parts, it's just going to reduce the overall time for commissioning. And it can also be used when you need to update the system in response to new components. Okay, so let's move to the next topic and think about how we can find anomalies, which are differences between what's expected and what's observed. And those anomalies can help us reduce the downtime that we see and therefore increase the overall equipment effectiveness. So in order to find anomalies, we're going to use simulations running in parallel with real-time operations. So one way to think about this is take this very familiar feedback loop, but instead of the plant being a transfer function, perhaps it's a model, a simulation model of a physical system. And perhaps the reference, instead of being just a function of time, is a stochastic discrete event simulation. So how do we change the controller, the PLC, to have that physical or simulated plant react to the stochastic simulation? So again, we call it virtual fusion because we have a physical plant running in parallel with a simulated plant. But here we have a simulated process running in real time, and we want to compare the simulation results with the plant floor data. So here we have two types of hybrid systems. One is we have continuous dynamics plus discrete event systems. And the second hybrid challenge is that we have the physical plant and the virtual model. So I'll talk a little bit about both of those hybrid challenges. I mentioned earlier that we use Matlab and Simulink. So here you can see a SimEvents model of a stochastic simulation where within each block, which is a stochastic state, we trigger the continuous dynamics that are also running in Matlab, so in the same simulation environment. And so we can do that pretty straightforwardly in Matlab. As I mentioned in the virtual commissioning, we need to keep track of time. And so again, we're using this Rockwell Automation SimKit to synchronize the time between the simulation that's running and the plant floor, which is running, of course, with the time clock on the wall. I talked already about the type of data that we're gathering from the plant floor. So once you have this data from the simulation and the data from the plant floor, how do you know what's different? It's stochastic, right? It's not deterministic. So you need to have some way to look at how do I determine the differences. And that's one of the challenges in this area is challenges in anomaly detection. So one thing is that there's process variability. We talked a little bit about the stochastics on how much time each process takes, but even within a specific state, during the transient, when the machine is getting set up to cut versus when it's actually cutting, those are very different types of signals that would be difficult to compare. When we have interactions between the tool and the part, if the machine is drilling versus milling, the data is looking quite different. And finally, we've mentioned already the data collection and the storage needs for large data. So what we've done in this example I'm going to show you about is use a modeling framework where within each machine, we look at global operational states. And we divide this state into 4 different parts. There's the functional state, which tells you whether the machine is idle or being set up, being repaired, or it's processing. There's the dynamic states that relate to the machine dynamics. Is the slide accelerating or decelerating, or is it moving at a constant velocity, or it's stopped, which would be a 0 constant velocity. I mentioned briefly the interactive states. Is the tool roughing or finishing, face milling or drilling? All these different kinds of interaction states will have different data characteristics. And finally, the process descriptors. What type of part is it? What type of tool is it? What type of material? And all these things will relate to the global operational state. So to determine these different states, we use expert knowledge of the process in some cases, but because of the stochastics, these times take different amounts through every process, through every cycle. So we use automatic event detection and dynamic time warping to separate the different states. And I'll show you an example of that. But this is really one of the challenges when you start diving into the data at a low level. So I'm going to describe this through a case study. So this is a project that we were doing with one of our industrial partners. And you can see that the car bodies are on carriers. So those, the car bodies are pretty obvious. Body in white is before they've been painted. And then the body carrier is going along. And you can see that the body carrier could be on 2 rollers that are in the same conveyor, or 1 roller from the back conveyor and 1 roller from the front conveyor, because they're moving along to the left, as indicated by the arrow. So you have this cycle time where the bodies are coming along, but they have these different states within each cycle. So what type of data do we have? I've listed some of them there, and I've put in bold the type of data that I'm going to use in the case study. So we're going to use whether the conveyor is processing or not. We're going to use what's the velocity of the conveyor. Is it accelerating, decelerating, or constant velocity? And then from an energy usage, we're going to look at what's the current being drawn by the motor of that conveyor. You can see each conveyor segment has its own motor that's driving that conveyor segment, and then the overall conveyor is to put all these different things together. So when we sat down to define what are the global operational states, as I mentioned before, there's the 4 categories. The functional is either processing or idle. The dynamic is related to the velocity of the conveyor. Interactive is whether the vehicle is on the rear wheel of the conveyor, on both the carrier is on the rear wheel, both wheels are only the front wheel. And for this particular example, we didn't use descriptive because all the data we had was for the same type of car. But you could imagine for different models, they would have different masses and you would expect different outputs. So what we did is over each cycle, we looked at the current from the motor over time. And you can see here a sample of a normal cycle where we've broken down these global operational states with these red vertical lines. The top table shows you what are the global operational states. For example, in global operational state number 1, the conveyor is processing, it's accelerating, and the part is out of the front and the rear. So, and then when it goes to the global operational state number 2, the part is only on the front, not also on the rear. It's still accelerating. And then it goes to constant velocity. And you can see that the current characteristics change over time throughout one cycle. So this is one cycle, one car going through one conveyor. Now, we got this data from one of our partners, and you could think of this data as being a model, right? So we're going to want to compare data coming off of the current system with this model, which is described by this set of current traces. So we also got some traces that looked like this, where there's some backlash in the conveyor. And you can see the indication of backlash only comes in this global operational state number 1. The current trace within all the other states looks fine. There's only this one anomaly within one of the states. So when we looked at trying to do anomaly detection, or taking the data from one state, comparing it against historical data for the model, if we built a classification model using machine learning to separate those that had backlash versus good states, you can see we got this, separator, and we got 60% agreement between what was good and what was bad, which is not great. I mean, it's better than nothing. It did give us some level of signal, but you can see there's a lot of backlash, those red triangles above the green line, that didn't indicate that there was backlash there. So we would miss those. and not be able to point to the operator that there's a problem in this conveyor, and you need to go look at the gears might be worn, and this backlash is going to cause some problem down the road. So what we did is, if we only looked at the data within the global operational state number 1, by separating out those different global states using event detection and time warping, as I mentioned, we were able to get to 92% classification. And so the message that I want to say is, by looking very specifically, not within the whole trace, but separating out the trace into the relevant states, you can do much better anomaly detection within a process that can help you reduce. Once you can find the anomaly, then you know what to fix. And this is, I think, a general message for machine learning. It's really great if you know what you're looking for. So once you can separate out what you're looking for, you can get really good identification. Another thing you can do is look at productivity analysis and look how much time does the system spend in each of those global operational states. And here you can see just one of them in global operational state number 4. When the bearings are worn, it takes about a half a second longer. Now, a half a second longer over the full 20-second cycle time might not be that noticeable, but a half a second over an average 1 second time within that sub-state is noticeable, and that can help you identify, again, anomalies, differences between what's typical and what's observed that can help you reduce the overall downtime. So this gives you a couple of examples of things that we've done recently, but I would just like to challenge you. There's a lot more work to be done in how can you model these systems? How do you determine what's the level of anomaly? How do you minimize the false positives and false negatives? You want to detect as many errors as possible, but not, sound the alarm every 10 seconds, because then people will turn it off. So trying to distinguish the true problems from the noise, as well as detecting the root cause. And I think in order to do that, you need expert knowledge and models together with large amounts of data. And I think that's a theme I've heard many times over this week at this conference. It's not just about data. Yes, data is really important. You need a lot of data, but without a model or an insight or understanding of the system, data is only going to get you so far. And then finally, I've only gotten to the point of detecting those anomalies. How are we going to generate the control signals to compensate for those deviations? If we see some anomalies in the worn bearings, should we just crank up the current on that motor for a while to keep it running at the same speed? What's the level of tolerance you have between driving it till it breaks versus taking it offline and not making any parts for a while you fix it? And how do you build that maintenance into your overall scheduling? So there's lots of challenges here that I'd like to encourage many of you to work with your colleagues. As we saw in the early map, there's a lot of important manufacturing challenges all over the world, and I think it'd be great to see more controls people working on this. So let me just wrap things up here. And I'll show you this little video that a student of mine made a few years ago that's sort of futuristic, that in the future, maybe you have this simulation model of your system where you can see in virtual reality everything that's happening on the plant floor. Not just what's happening physically, but also what's happening virtually. Can we see that data essence in the virtual world, just like we can see the physical essence in the real world? Track the part numbers, the quality, the history, and then can we use that to improve, as we talked about, rapid false diagnostics, reduced downtime, improved overall effectiveness to lead to improved profitability. So we see this future vision where we're taking all the data from the plant floor and pushing it to the cloud. And as I mentioned, this can be done today. It's hard. It's still kind of cutting edge to do it, but it's possible. But once you have it there, what are you going to do with it? How do you incorporate simulations? Can you take the data from the simulations and also put that in the cloud? Is that another way of looking at historical data or potential data? Or can you run the simulations forward to evaluate different possibilities? So we want to be able to create these models automatically by merging simulations and data, and then automatically adjust the machines. Right now, what we've done so far is build what we see in the upper right. We take the data, we identify the anomalies, we put it in a spreadsheet, and we show it to the operator. And we assume the operator is still there and has some knowledge, but we'd like to be able to either give that operator advice on what would be the best way to address that, or maybe even make some changes automatically. So I think there's a lot of opportunities there. So in conclusion, I'd like to acknowledge all the work of the current and former students who did things that you saw in this presentation. Obviously, this is never something that a professor does all by his or herself. And of course, the collaborators. Professor Keir Barton, I believe, is out there somewhere. Can't see anybody. And then Dr. Maturana from Rockwell Automation has been a great collaborator and working with the tools and things that they have, as well as Dr. James Moyne at the University of Michigan. And of course, the funding that makes it possible. So that's the end of my presentation. I thank you very much for your attention, and enjoy the rest of the conference.